Alright, so we are looking at conservation of momentum for this lesson. So we're going to understand conservation of momentum in a few different scenarios. We're going to look at just general conservation when things collide and stick together. And then we're going to be looking at recoil scenarios. So the bell ringer question for the lesson. So we have ticker tape patterns or dot or particle diagrams of three different football players. We have a halfback who's 60 kilograms right there, and we have a tight end who is 90 kilograms, and a lineman who is 120 kilograms. And running down a football field to consider these patterns, let's try to find our velocities or compare our velocities and then compare our momentums. Okay, so compare the velocities. How many times greater are the velocity of the halfback and the velocity of the tight end than the velocity of the lineman? Okay, so we have to kind of look at what we're given here. So we know that this one's 3 meters per second, and we can kind of pull apart that each of these is 3 meters per second. So then this is 3, 6. So we're covering 6 meters here in 1 second, because remember, we can consider each one of these 3 meters per second. So 3 meters per second, 3 meters per second, 3 meters per second. We're traveling 3 meters each second. So this tight end is traveling 6 meters in each second. So now we have to use what we found with our lineman to do the halfback. So we went 3, 6, 9 meters. So 9 meters in 1 second. So this would be 9 meters per second. Okay, so how many times greater are the velocity of the halfback than the velocity of the tight end than the velocity of the lineman? So halfback would be 1.5 times the tight end, and it would be 3 times the lineman, and the tight end would be twice as fast as the lineman if we're comparing these numbers. So which player has the greatest momentum? So in order for us to figure that out, we have to take, so remember, momentum equals mass times velocity, and we'll have to find that for each one of those. So we'll find it for the lineman, we'll find it for the tight end, and then we'll find it for the halfback. Okay, so lineman is going to be 3 meters per second times that weight, or that mass, excuse me, 120 kilograms. All right, and the tight end is going to be 6 meters per second times 90 kilograms, and the halfback is going to be 9 meters per second times that mass, which is 60 kilograms. So we're going to put all these in our calculator and see what we get. So our lineman was going 360 for his momentum, 360 kilograms times meters per second. Tight end is 540, and the halfback is 540. So the lineman actually, you might think, has the greatest momentum because that's the biggest person, but that's not true because he's going slower than everybody else. So lineman's got 360, tight end's got 540, and halfback's got 540. So that's how we compare those momentums in this scenario. All right, so let's jump into our lesson now that our bell ringer is completed. Okay, something to think about when we're talking about momentum is recoil. So what is recoil and how is it useful? So think about recoil, and you've probably heard this word before in our scenario here, maybe in a physics or physical science class. It'd just be two carts colliding and then they bounce apart, okay, or sometimes they stick together. So for this scenario, they would be bouncing apart, and we have some things going on when they collide, actually before they collide, when they collide, and after they collide. So recoil is essentially just things kind of bouncing away from each other. So the most common thing you hear about might be a gun, and when you shoot a bullet, the recoil from the weapon kind of jolts you in the shoulder, and they develop guns, they developed stocks on rifles and such to help it so you don't have that serious recoil. And some things we're going to cover here, some vocabulary, would be closed system, isolated system, law of conservation of momentum, and law of conservation of angular momentum. So we'll be talking about the basic law of conservation of momentum in this lesson, and this will be in the second part of the lesson when we look at the angular momentum of objects. So what is a closed and isolated system? A lot of the time in physics we talk about closed and isolated systems because that's the easiest thing to take care of. There are no outside variables. So a system which does not gain or lose mass is said to be a closed system. Okay, so something that might not be a closed system, you might have two cars that kind of run into each other. This is probably the most common momentum scenario. Two cars run into each other and the bumper falls off of one of them when the car recoils or bounces back. That would not be a closed system, but we could kind of account for that. There are ways to account for that. Bumper falling off just to kind of make it a little bit easier, but closed systems are the simplest to calculate. Okay, and then an isolated system doesn't have any external forces acting on it, so that means we wouldn't account for air resistance or drag or I don't know, maybe there's a third vehicle involved, but we're just looking at these two vehicles for a scenario, maybe left and right, and the third vehicle comes in from this direction. So isolated system has no external forces acting on the system, which is just no outside forces, which 90% of the time is probably drag and friction or things like that. So, law of conservation of momentum, this states that the momentum of any closed isolated system does not change. So what that means is we can look at the before and after momentum and they should be equal. All right, so here is our equations. Law of conservation of momentum would be final momentum equals initial momentum, and these are interchangeable. If you want initial equals final, that's fine. But just to give kind of a visual to it, we have two particles over here. One is obviously smaller than the other, but we could calculate the momentum of this particle and the momentum of that particle. This would be our initial, okay, and then this would be our during, so particle C, particle D here is what that should have been. Okay, so momentum of C, momentum of D, that should maintain when these two collide. So at the instant they collide, the energy that they're going to be getting out of the momentum will give me my final momentum of each of the particles. So we could consider this initial momentum of particle C and initial momentum of particle D, and this would be final of each of them. So we could take this initial scenario and calculate whatever we wanted to in the final scenario. All right, now it would be obvious just to kind of measure them with a camera or something like that. It's a high-speed camera, but if we look at things on a microscopic level, it might be a little more difficult to do that. Or maybe we want to project what's going to happen given the certain mass of a vehicle or something like that. So we wouldn't actually want to crash vehicles together. We can use the information to find final or, I guess, initial. So in forensic, they might be using some final information to find initially how fast a vehicle is going. And in maybe testing with crash dummies or something like that, they have an initial speed and mass, and they might want to find the final speed and mass after some kind of a collision. So law of conservation of momentum applies in a lot of places in our lives. Okay, any kind of testing is going to use this, and any kind of I guess observation, testing of collisions and observations of collisions, anything that bounces or hits something is going to use law of conservation of momentum. Okay, so we are going to apply the law of conservation of momentum here and figure out a couple scenarios. So a 1,875 kilogram car is going 23 meters per second, rear ends a 1,025 kilogram compact car going 17 meters per second on the ice in the same direction. The two cars stick together. How fast do the two attached cars move immediately after the collision? So let's draw a picture here. So we have our 1,875 kilogram car here, and then let's just draw this little compact car. So that one is 1,025 kilograms, and it says that they are both going, so this one's going 23 meters per second, and then this one is going 17 meters per second, and it says on the ice, so that's just so we can kind of neglect friction. So things are a lot easier, right? This is a closed system, closed isolated system, so we can neglect friction here. they're both moving in the same direction. So let's declare this direction to be positive. So both of these velocities will be positive. Okay, so let's write our conservation of momentum equation here. We have final momentum equals initial momentum, and I like it the other way around. So let's do initial momentum equals final momentum. So initially we have these two cars. Let's call this car 1, car 2. So we have the momentum of car 1 and the momentum of car 2. We want to add those together because we want momentum of that total closed isolated system. Okay? And then in the end, again, we're going to have momentum of car 1 and momentum of car 2. However, let's look at this here. So the two cars stick together. So we could, I suppose, have them separated like that, but it's going to be a little bit of a trick here because remember, momentum is mass times velocity. However, when they stick together, it's going to be mass of car 1 and mass of car 2 times that final velocity. So this is kind of a trick here to doing conservation problems when things stick together. If they bounce apart, then you would do it like this, where you have the car 1 final plus car 2 final. But they stuck together, so this is what we got to do. So let's start filling things out. So again, momentum equals mass times velocity. So we have momentum of car 1 plus momentum of car 2. So our momentum for car 1 is 1875 kilograms. And that car is going 23 meters per second. We got car 2, which has a mass of 1,025 kilograms, and it's going a speed or velocity of 17 meters per second. Okay, so that's the left side of the equation. Now let's fill out the right-hand side of the equation. So that's just going to be mass of car 1 plus mass of car 2 times that final velocity, which we don't know. That's what we're trying to find here. We're trying to find that final velocity. So now we can do a little bit of work here. Take those two, multiply them, take those two, multiply them, and add them together. And then we get 60,550 kilograms times meters per second for our momentum on the left. So this is my initial momentum of the system. Okay? And then we have 2,900 kilograms, and we add those together, times final velocity. So we'll have to divide both sides by 2,900 kilograms. And you can see what's going to happen with the units here. So kilograms are going to cancel out, and we'll be left with the meters per second, which is what we're looking for in the end. So we take 60,550 divided by 2,900, and we get 20.88 meters per second. So after they collide and start moving together, they're both going 20.88 meters per second. And we can kind of look back at our numbers that we started with. We had 23 and 17, so it kind of makes sense that we should be in between those two numbers. Okay, so we're not directly in between, but we're close. So let's look at another scenario down here. So we have the same two cars, but they're going in opposite directions. So let's draw our car from above. It's a little bit bigger now, that's okay. So that car is going 23 meters per second. Let's call this the positive direction. All right, and that's car 1, which is 1875 kilograms. Car 2, that's our little guy, compact car, is going that direction. 17 meters per second, and that's our 1,025 kilogram car. So this will change our numbers a little bit. It's going to change mostly positives and negatives when we look at initial momentum, and we'll see what we get for our final velocity here. So they do stick together again, so that's going to be similar to what we had up above, where for the final one we're going to have mass of car 1 plus mass of car 2 times that final velocity. So the initial momentum, that's just mass of car 1, velocity car 1, plus mass of car 2, velocity car 2. What's going to be different here is that number, when I plug it in, will have to be a negative because they're going opposite directions. So we have to pay attention to the direction of the motion here because velocity is a vector, so we have to pay attention to the magnitude and direction. So let's start throwing our numbers in here and let's see what we get. So we have car 1, which is 1875, going 23 meters per second. Car 2, which is 1,025 kilograms. And now this is the one we want negative 17 meters per second because it's going the opposite direction. And then let's just write that 2,900 over here again from the last problem times final velocity. Now this number is going to be a little bit different, but then again we're going to divide by 2,900. So on the left hand side we get 25,700. That's kilograms times meters per second. And then we have that 2,900 on the right. So divide both sides by 2,900. And that's kilograms, just so we can kind of maintain our units here. So we'll end up with a meters per second. So when we divide by 2,900, our final velocity ends up being 8.86 meters per second. Okay, so this one's a little bit harder to kind of project the numbers. Now you might think that, well, I can just take 23 and minus 17. Well, that's not the case because that's not going to give us exactly how fast the vehicles are going to be going when they collide and stick together. Okay, so there is a problem using conservation of momentum when the two vehicles stick together. And we can also use conservation of momentum when the two vehicles bounce apart, but like I said, it would be something like this, where they're separate. Okay, and that's like final, and then final there. So these would be like initial quantities, and these would be final quantities of momentum, and this would be after they separate. So another type of momentum that we talk about is recoil. And it's still just momentum, but it's just in a different scenario. So conservation of momentum can be used to explain situations with recoil. So a pretty easy scenario to consider would be two skaters on the ice. Pretend two people are standing together, or two people with regular inline skates, either would be fine. They're standing together in an ice rink, and they're going to push each other away. When they push each other away, so you have skater 1 and skater 2, there's going to be, just say one person pushes them in the scenario, they're both going to bounce away from each other in opposite directions, right? So we have the push there, the force, and then this would be the recoil from that force. So they're standing together, then they push each other, and they go apart from each other. So here, initially, the momentum is going to be 0 because they're standing together. So afterwards, the momentum needs to be 0 as well. So the momentum of, let's call this person 1, and momentum of person 2, if you add those together, then that should be 0 as well, because our initial was 0 because they were standing at rest. Okay, so think of a cannon or something like that. Cannon has, okay, so cannon here has the ball in there, and we have the fuse there. You ignite the fuse, everything goes through there, then there's an explosion here, and the ball goes flying out. Okay, right here beforehand, the initial momentum was 0 again. But we know for a fact, we know for sure, because you wouldn't want to get hit by it, after the ball or the cannonball is out here, still going that way, then your final momentum is definitely not 0. Okay, but if we look at the entire system here, so this would have to take the explosion of the gases explosion with the ball going that way. The final momentum of that would have to be 0 kilograms times meters per second if we looked at the whole system. Okay, this one's a little bit more complicated than this scenario here, but regardless, we're using conservation of momentum to figure it out. Okay, so total momentum of the system is 0 before and after, so it's got to be 0 throughout. So this would be kind of a recoil scenario if we took the final velocity momentum, or not we took the mass of the first object times the final velocity is equal to the mass of the second object times the final velocity, but it's negative because it's in opposite directions. So this would be a recoil scenario. And if we just kind of made it, I'll show you here. If we use conservation of momentum, I can show you how we get this. So we have initial and final. Let's say we have two objects, mass 1 and mass 2. This would be our initial momentum. And then our final momentum, we have mass 1 times the final velocity plus mass 2 times the final velocity. This is going to be 0. Let's say that's 0 kilogram times meters per second. So then if we have, let's write some equations here. We have 0 equals mass 1 times final velocity of mass 1 plus mass 2, final velocity of mass 2. Then we can solve this equation. So we can move this to the left, we can move this to the left. Either way, one of those is going to be negative, so we write it out like this. So mass of object 1, or this would be final momentum of object 1, is equal to the final momentum of object 2 is equal to the final momentum of object 2, but that's in the opposite direction. So that's where this equation comes from. This is recoil momentum. So a scenario, this is kind of a rocket science scenario for you. So rocket fuel is in a closed, isolated system, and that's an easy way to calculate how things are going to work once we send a rocket up in space, or before we send a rocket into space. The fuel is in a closed system. So we have fuel and some kind of an oxidizer, because the fuel has to have oxygen in order to ignite. So we have fuel and an oxidizer to combine in a rocket motor, and we ignite the fuel, and hot gases leave the exhaust of the engine, and that's what propels the rocket forward. So if you think of any rocket videos that you've seen, usually you have a ball of hot fire, or this would be your hot gases there, and your rocket is getting propelled up, and gases is getting propelled down. And that's how this actually goes up, because of the hot gases going down. Okay, so these would propel that rocket upwards. So thinking of Newton's laws here, we have Newton's third law in action here. So that is, for every action, there's an equal and opposite reaction. So the gases pushing that way, rocket going that way. Okay. Another scenario would be maybe shooting some kind of a gas gun in outer space, or we have an astronaut. Maybe they use these guns to get to where they want to go, or they have a tube coming from their oxygen tank or something like that to expel hot gases or expel gases away from them. Okay, so they're going to pull the trigger, which is going to put gases out of that little gun, like our scenario down here, and that's going to make the astronaut go that way, and the gases are going to be going this way. So now look at the vectors here. This vector is a lot bigger than that vector, right? Think about why that is. This is the vector for the gases, and this is the vector for the astronaut. So in order for me to get that equal and opposite momentum, or actually to get this astronaut to move, those gases have to be going quite a bit faster, because the mass is so small, right? So we have a tiny mass. We have the masses of the gases here, and that's going to take my astronaut and move them at a fairly slow velocity, because the mass of the astronaut is quite a bit bigger than the mass of the gases. So a type of propulsion that's being tested out a little bit right now is called ion propulsion, and I have a link here if you wanted to check that out. But essentially it uses ions and magnetic fields, and it propels ions. So pretend this is the back of a rocket. It's going to propel ions out the back of the motor. So if you don't know what an ion is, it's either a positively or negatively charged particle. So it's going to use some kind of a magnetic field here. So this would maybe say we have a negative charge, because we know that like charges repel. So we generate some kind of a magnetic field here, in this scenario a negative field, and then we'd have some kind of a chemical that is an ion, And this field here is going to push those ions out the back of the motor, which is going to cause a velocity of those going that way, and it's going to cause a propulsion of the motor going that way. So if you want to check it out, there's a link. You can Google that link. So let's look at some examples using recoil momentum. All right, so we have an astronaut with a little gun here. He's got a gun that fires gases out, a thruster pistol. So that expelled a quick burst of 35 grams of hot gas at 875 meters per second. The combined mass of the astronaut and the pistol is 84 kilograms, so we have that much of the gas going out at that speed, and then we have a total combined weight of the astronaut and the pistol of 84 kilograms. How fast and in what direction is the astronaut moving after firing the pistol? So recoil momentum is going to be the final of object 1 is going to be equal to the final of object 2, but negative because they're going opposite directions. Okay, so we have to follow law of conservation of momentum. If we wanted to write that out again, remember we have initial equals final, and our initial is going to be 0, and our final is going to be mass of the gas times the velocity of the gas plus mass of the astronaut times velocity of the astronaut. And we would solve this around, so we can move this around if we want to. It depends on the way we wrote this, but I wrote the gases first and the astronaut second. So we would have the gas here, it would be the negative, and then the astronaut would be the positive here. So let's go ahead and use this equation and plug everything in and see what we get. All right, so the mass of the gas here is 35 grams. So you want to change that to kilograms because we have kilograms here. All right, so we have a negative. The mass of the gas, change that to kilograms. So remember there's 1,000 grams and a kilograms. We move that decimal place 3 times. So 0.035 kilograms times the speed of the velocity of that, 875 meters per second. And we're going to need to make that a negative 875 meters per second because our velocity vectors are going in the opposite direction. We have to think about what direction things are moving when we're done here. All right, so that equals the mass of the astronaut with the gun. Okay, so it's given to us a nice number there sometimes. And this doesn't say astronaut and pistol and gas. It's just the astronaut and the pistol is 84 kilograms. So this is after everything is done. All right, and we don't know the final velocity that astronaut is going when we're done. So let's solve this here. We're going to divide both sides by 84 kilograms over here. All right, so that takes care of that. We have a double negative here. That takes care of itself. And now we put that in our calculators to see what we get as a final velocity. So the astronaut is moving 0.36 meters per second after he fires that gas. All right, so the velocity is much smaller because he's much more massive than the gas that's flying out of the gun. All right, so let's look at another scenario here. We're changing some things around. So what if the same astronaut in example problem 4, which is the one above, had a mass of only 62 kilograms with the pistol? What would be the final speed of the astronaut? All right, well, let's write down what we had before. So we had negative, mass of the gas was 0.035, and it went 875 meters per second, but it was negative because it's going opposite direction. And then our mass of the astronaut is 62 kilograms. And let's find that final velocity again. So divide both sides by 62 kilograms to see what we get. So our final velocity is going to be 0.49 meters per second. So that makes sense if we compare it to that number up there. It's a lighter astronaut, should be going a little bit quicker after they fire their thruster pistol. Okay. So another example could be if you have two people standing together, maybe they're on a skateboards or something like that, and they push each other. So the initial momentum here is 0, but then when they push each other, they're both going to fly in opposite directions. So we'd be able to figure out, if we knew how fast one of them was going, if we knew their mass, and how fast one of them was going, then we could figure out the velocity of the second one. So there's a lot of recoil scenarios that this would be helpful for. Okay, so hopefully this helps out understand recoil. So we use conservation of momentum to figure out recoil scenarios, and we can find masses if we want to, but then consider the equation. We have mass and velocity of one item and mass and velocity of a second item. We need to have 3 of these in order to figure out the 4th one. So in recoil scenarios, you're usually going to be given 3 of those, and you will find the 4th one. Okay, so this could be helpful if we knew the mass of a gun or something like that. We could figure out how much recoil or how much velocity a gun is going to have, or a bullet would have. 2 vehicles crash and bounce apart. We could use that. We could use recoil scenarios for that. So forensic science or something like that, or criminal justice, trying to figure out how fast cars went before and after a collision. That's kind of helpful for this. So here is your lesson in momentum with collisions and conservation of momentum. The next part will be conservation of angular momentum and more practice using this stuff. So hopefully this makes sense. Let me know if you have questions. Thanks.